Welcome again in the VLSI technology lecture. In the last lecture, we have started with the optical photolithography, in which I have explained about the very basics of optical lithography. And I split the complete optical lithography system into three various parts, in which I told you about the light sources in the last lecture. So in the today's lecture, our main aim is to discuss about the our next topic, which is our photo mask. So let's begin the discussion. So as I explained you, in the case of optical photolithography, so you just see this system, you try to recall this system. This system I explained you that first of all we need to means feed our requirements of the mask, okay, basically requirement of our IC, okay, in which we have to give the input to this system about the various features of the ICs, like what is the minimum feature size, what is the minimum distances between the two elements, what will be the overlapping between the elements that may be allowed. And based on those features, a particular software or the CAD tools can be used for making the mask. So first step is to fabricating the mask. Okay, because in the optical lithography system, it is very much necessary to having a mask, and that mask is actually designed based on the following a certain layout design rules. So that is actually based on the CAD tools. Okay, so CAD system will take care of it, and then we have to first design the mask, and after that we have to go for its fabrication. So today we have to look at how this photo mask actually fabricated, and what are the different ingredients of the photo masks that we have to look at. Okay, so then we have to go for the material details. Okay, so first of all, you can see this is our system. Okay, first you can see in the first picture, this is our computer. It is doing just designing part. Okay, and after designing we have to go for the fabrication part. So in the fabrication part, you can see we have various systems like Electron, e-beam technique we are also having a direct ledger writing techniques. Okay, so here I'm just showing one of the system. Okay, so you can see that the pattern that we want to transfer onto our wafer, okay, that pattern has to be there onto the mask, because in the optical lithography, whatever is the pattern onto the mask, that pattern will be going to be printed onto your wafer systems. Okay, so first of all we have to fabricate the mask itself. Okay, so in the mask, you can see in this picture, this picture is one of the picture of photo mask. So this is our light filled photo mask. So first of all, we need to understand that what are the different materials that we have to take for making the photo mask. Okay, what are the various steps, what are the different materials. Okay, and then how it will be fabricated. So that we have to look at. So basically nowadays, for fabricating the photo mask, we are using the fused silica. Okay, so as we are having the photo in case of IC fabrication, we are having a substrate. Here is substrate is nothing but your fused silica. So onto the fused silica we have to deposit a layer of chromium. Okay, so basically we have to deposit the layer of chromium, and then a particular resist is actually laid down onto the chromium layer. Okay, so that we have to put on onto the chromium layer, and again we have to go for the direct writing technique. Okay, so direct writing technique we have to perform, and then we have to remove a certain portion of the chromium. Okay, we have to remove the certain portion of the chromium by using the optical photolithography. So again we have to perform the somehow we have to perform the lithography operation again, but this technique is a direct writing technique. So in case of optical photolithography, that we are actually doing onto the wafer, in this case what we are having is we are having a photo mask. Okay, we are having a photo mask, and then we are having a light source. This light source is actually passed through the photo mask, and those regions which are the transparent for the light, that through that particular regions, your light will penetrate through and it will go to the wafers. So means wafer, that wafer is carrying the photoresist. So by that way, this photoresist is actually going to be gets hardened or softened based on the what type of photoresist we have applied onto the wafer surface. And then we have to use a particular developer solutions, and that developer solution can selectively remove your photoresist, and then we can further remove the underneath layers of SiO2. And after removing the SiO2 layer, we can remove the photoresist, and then we can uh, uh, go for the next process like diffusion or adding the dopants. Fine. So that way we can do the our process. But in the case of photo mask, okay, when we are talking about the mask making, okay, in this mask making, we do not have any other mask, okay, it is a direct writing technique. So that direct writing technique is our, either it is laser beam, we can directly use the laser beam for writing this small features onto the chromium layer, okay, or we can use the electron beams. So these are the two techniques that we can use, or they are actually most prominent nowadays. So first of all, we have to look at what are the different materials. So as I said, basically it is nothing but a fused silica, and onto the fused silica we are having the chromium, okay, and then this chromium is actually containing a a photoresist, okay. That photoresist can also be like a electron resist, it can also be an electron resist, okay. So either it can be means sensitive to electron beam, or it can also be sensitive to your like laser beams. So basically some other materials are also being used for like your photo mask. So basic types you can see here, it is like photographic emulsion on soda lime glasses. So they are very cheap, okay, but the quality is not that good, okay. Photographic emulsion on soda lime glasses, like in earlier days, this Fe2O3 on soda lime glasses was also used, but the most prominent is your chromium on soda lime glass or on quartz glasses, okay. This is the most popular one, right? So as I explained you about the certain properties of the photo mask, if you remember, that the photo mask should have a very small means thermal expansion coefficient, okay. It should not be expanded when we expose through a UV rays, because UV rays is hitting your wafers, right? So it will hitting your mask also. So when it will increase its temperature, then the features that is printed onto the photo mask, it should be stable with temperature. It should not like that if the temperature is rising of your mask, then because of the rise in the temperature, if features are getting means unstable, or it is expanding, or the gaps between the different features are changing, then it is of no use. So that we have to take care while means choosing the material. So this chromium and the quartz actually having a very low thermal expansion coefficient. So that's why we are using it. Fine. Then you can understand that actually basically in this system, okay, when we are making the photo mask, here you can see this is the example of the light filled photo mask. So as you can see in the light filled photo mask, we can define the photo mask based on its polarity. So either it can be a light filled photo mask, or it can be a dark filled photo mask, okay. So when we say it is a light filled photo mask, it means that most of the region of this photo mask is transparent. You can see here in this picture that most of the part of this light filled photo mask is transparent. Okay, so light can penetrate through, but you can see there are certain portions which are opaque. So these are nothing but your chromiums. Okay, these are your chromium layers. Okay, so these are your chromium layers. So this is your light filled photo mask. We can also have the dark field photo mask. So in the dark field photo mask, what happens is most of the part will be opaque, and certain portion will be having your transparent regions. Okay, so you can think of like this, all the transparent layer will be filled with your chromium, and that will be a dark field. Okay, obviously because light cannot penetrate through your means chromium layer, and wherever the chromium is present in this case, it will be having a transparent region, okay, through which the light can penetrate. So that way we can have either a light field photomask or we can have the like dark field photomask. Fine. So now we have to think of actually while fabricating this one. Okay, I will explain you how it can be fabricated. So before that, we have to look at one more very important factor about it, about the mask. As we know that whatever the pattern that is we are printing onto the mask, okay, whatever we are images printing onto the mask, this image is going to reprint onto your wafer. So any defect which is available onto the mask, okay, any defect, any kind of defect, if it is available onto the mask, the same defect is going to be printed onto your wafers. So if defect is there onto your mask, obviously your wafer cannot be correct. Okay, whenever you are exposing your wafer, whatever ICs you are going to make, that wafer or IC is also having or carrying that particular defect. So while fabricating the mask, we have to take the utmost care. If you are not taking it utmost care, then defect will be replicated in into your wafer. So that we have to take care. Fine. So one thing which is very important about the photo mask is that as you know that when we are placing a photo mask, for example, if we want to expose the wafer, okay, while doing the optical photolithography, and let us say we have fabricated a certain photo mask by using a certain technique, maybe it is a laser beam technique or it may be a e-beam technique, okay. So by whatever way we have fabricated the photo mask, let us say, and if we keep this photo mask in this region, and then if we expose the wafer, let us say we want to expose the wafer, then there is a chances, okay, whenever we are dealing this type of system, it must be kept in a certain environment. If the environment is containing a certain dust particles, then there is a chances that the dust particle may sit onto your mask also. So once a dust particle you can think of, because we know that the feature side that we want to draw onto the wafer is of in the microns or sub-microns regions, or you can say it is in the nanometer, okay, range, like 14 nanometer, 10 nanometers we are talking about. So that time a very small particle, okay, of very small size or small dimension may also affect the system. Okay, it also affect the system, because if it is sitting onto your mask, then the image of this mask is going to be transferred to your wafer. So we have to take utmost care while doing a wafer exposure. So that we have to take care of. Okay. So to prevent such problems, okay, to prevent such problems, you can see here, basically you can see this reticle word is used for the substrate, the quartz substrate that we are using, the fused silica quartz substrate. Okay. Fused silica substrate here, the same substrate you can say like a reticle also. Okay. So onto this fused silica uh, uh, quartz, or you can say it is a substrate, onto this substrate what we have to have is chromium pattern. Okay, so we are having a chromium pattern, and then we are having a metallic frame. Okay, and metallic frame is there, and onto this metallic frame we have to stretch a particular pellicle film. Okay, so this pellicle film is a very thin membrane, okay, which is made up of nitrocellulose. So what is the function of this nitrocellulose or this thin membrane? The function of this thin membrane is whenever we are using the your this particular mask at the time of optical photolithography, at that time if any dust particle will sit onto this, okay, then it will not go to the chromium. Okay, it will be having a certain set of offset from the chromium layer, because this particular means your pellicle film is actually having a height around some mm. Okay, so it is not like it is just onto the chromium. First of all, we have to make a certain metal frame, and that metal frame is having a certain height, and onto that metal frame we have to stretch this pellicle film. Okay, and the function of this pellicle film is that if any dust particle is actually coming to this particular mask, then it will not go to the chromium, but it will be available onto the pellicle film. So based on the focusing mechanism of your lenses, okay, this can be kept out of the focus. Okay, out of the focus, that can be taken care of by the optical system. Optical system that will be used for your exposing the wafers. So by keeping this out of the focus range or the focal range of your lenses, this particular image cannot be transferred to your wafer. Okay, so that cannot be transferred, so that we have to take care of. Okay, so this is what is the use of your pellicle film, right? So that you have to take care that we need to have pellicle film whose function is to uh, keep away the dust particle, right? And one more thing which is very important is about the anti-reflective coating. Okay, so all the lights should not like when it is we are shining the lights. Okay, so it should be like when the light is going through the transparent layer. Okay, in the side of that transparent layer, obviously we are having the chromium pattern. So this chromium pattern should contain the anti-reflective coating. Okay, and that completely means the light should be uh, means reflected back. It should not go like go and scattering. Okay, so that is the use of your anti-reflective coating, so that you have to remember. So this is our what photo mask is. So this photo mask is actually how it is fabricated, that we have to understand how it is fabricated. Okay, so the fabrication is nothing but your direct writing technique. Okay, so that you understand how it can be fabricated. So first of all, the photo mask, how it can be fabricated is like as I said, the chromium pattern on quartz, right? So photo mask is nothing but your chromium pattern on quartz. So how it can be fabricated? So it is similar to your photolithography. So try to understand it is similar to photolithography, but use a focused laser beam. Okay, it is a direct writing technique. No mask is needed. This is the basic difference. Okay, when we are exposing a particular wafer, okay, by using the optical lithography system, in that system we need to have a photo mask that is containing a pattern, and then the light will be shined onto the photo mask, and then the light will penetrate through the photo mask, and then it is its image is going to be printed onto your wafers. But here in this case, when we are fabricating the photo mask itself, then this is nothing but your direct writing technique. There is no need of photo mask. Okay, we are not having any photo mask, but it is a direct writing technique. So how we do it? So first of all, we are having a quartz substrate onto which we are having a chromium layer. Okay, and then onto this we have to means spread one photoresist layer. Okay, if it is a electron beam technique, then we have to means coat a particular resist which is electron sensitive. It is not photosensitive. Okay, it should be electron sensitive. So in this case, when we are having a quartz, chromium, and photoresist, then a very narrow focused beam should be applied. Okay, very narrow and focused beam should be applied. So like in the wafer exposure system, what we do is we are having large number of beams of the from the laser source, and then this beam will be actually going through your wafer photo mask, and it will be penetrating through the photo mask from those regions which are transparent to the laser beams. Okay, and then that beams will come out, and then it will be exposing your photoresist layer. But here it is not done, but here what it do is we are actually applying a focused uh, focused your laser beams. Okay, so light let us say we want to make a pattern at this point. Okay, so a very focused laser beam will be applied, and because of this application, obviously this region of your photoresist will get exposed. Okay, and after exposing this region only, after exposing it, obviously because it is a photoresist, its chemical property is going to be changed, right? So its chemical property will change, a particular developer solution will be used, and then this portion can be removed. Okay, so this portion can be removed. After removing this portion, again what we have to do is we have to remove the underlying chromium layer. Okay, so this chromium layer can be removed. So again we have to use a certain chemicals, and that chemical will be able to etch out your selectively etch out your chromium layer, and that way we can make the window at this point. Fine, and later on this resist can also be removed. So this way we can make any pattern. Okay, any pattern we can make. So this is how we are actually making the pattern onto your photo mask. So this is your direct writing techniques, okay, which is not required any photo mask. Fine. Similarly, we can also have we can also fabricate the photo mask by using the electron beams. Okay, so there is a there is a advantage of electron beam over the your laser beams, because electron beam is having its beam size which is of very small. Okay, it is of zero point 0.1 micrometer to zero point 0.5 micrometer, so it's very small spot size you can say, or you can say the beam size is very small as compared to your lasers, and that's why electron beam technique for fabrication of your mask is very much prominent. Okay, it is very much of importance. So that technique is we are using nowadays. Fine. So you can think of, because we need to miniaturize our circuit, so we have to have a very very small feature size. So to have this small feature size, we need to go for the e-beam uh, photomask fabrication. Fine. So so how it can be done by using the e-beam? Again, we need to have the e-beam source. Okay, and then a similar technique, the way we have used for your like laser beam technique, again we can, the similar way we can use the e-beam technique. Only difference is that we have to take the quartz chromium layer, and again onto this chromium layer the resist will be your electron sensitive. Okay, rather than the photon sensitive, it is now electron sensitive. This is the only difference that we have to take care. Okay, so this resist will be electron sensitive. Now, when it is having electron sensitive photoresist, then we have to apply a very focused electron beams. Okay, so let us say we want to make a pattern onto this. So a focused electron beam first applied, a particular pattern generator will be used. Okay, based on the design of your photo mask, when we are making a design onto our computer, okay, using the CAD tools or some other tools, then it will be having a pattern generation. Okay, so a certain very sophisticated system will be there that will be fed with a particular program, and that program will run a pattern generator. Okay, that will be generating electron beams, okay, in a particular fashion or particular pattern. Okay, and then this particular certain area will be exposed with the electron beams. So obviously this particular area only getting exposed. Okay, and after that there will be a certain chemical changes again occur into the resist. Okay, your electron sensitive resist, and then a certain developer solution again it will be used, and then this resist will be removed, and then we have to selectively etch out our chromiums. Okay, so this chromium can be removed. Now, after removing the chromium, we can remove the resist layer. Okay, resist layer can be removed. Now, after doing this, we have to be very ensure, we have to make it sure that the dimensions or the feature size or the properties of the mask that we have fed into our system, whether the same dimensions have been achieved or not after doing this removal of the chromium. So that measurement has to be done. Okay, so this critical dimensions has to be measured. Okay, whether the thickness of this means minimum feature size we have means the whatever be the thickness of this layer is achieved or not, or whether the minimum feature size is achieved or not, that we have to make the measurements. Okay, so once we do the measurements, we have to satisfy ourselves whether the properties has been met or not. If it is not met, okay, in that cases either we can go for initial cleaning if some defects are there or some contaminants are there, then we have to go for the initial cleaning. Then we have to look at for the defects. Okay, defects and inspections. So sometimes it happens that some of the chromiums are also getting removed. Okay, which is not desired. Let us say some of the chromium got removed from this portion, but it was not desired. So because some of the portion got removed, this type of defect is called as pinholes. Okay, these are the pinholes because this particular chromium layer we do not want it to remove, but it is happening because of the wrong pattern generation, you can say, or because of the misalignment of your this particular substrate to your electron beam generation. So due to maybe whatever be the cause, but if there is a pinhole which is detected, then we have to repair this particular mask. Okay, so either there could be a pinholes, means the extra chromium is already removed, or there may be a certain chromium layer which we wanted to remove but it has not been removed. Okay, so that is called as the chromium spots. Okay, so what I mean to say by pinhole, there is some chromium which is removed, we do not want it to remove it, but some of the in the case of chromium spot, some of the chromium is left out that we wanted to remove. Okay, so once this kind of defects are inspected, then what we have to do is we have to go for the repairing. Okay, so how do we repair it? We have to, in the case of pinholes, we have to deposit the extra chromium to these spots. Okay, some selectively deposition of the chromium has to be done. And in the case of chromium spot, what we have to do is we have to selectively again remove these portions. So once this repairing is done, okay, once we repair the our mask, then the next portion is, after doing this one, we have to go for the preparation of your you have to make the pellicle film. You have to stretch over the pellicle film over your chromium layer. Okay, so before that we have to go for the pre-pellicle cleaning, and then we have to stretch the nitrocellulose film. Okay, that is called as the pellicle film. Okay, so that we have to stretch over your metallic frame, and then finally we can got our uh, photo mask that can be used for wafer exposures. So this way we can fabricate our photo mask. The another way of making the photo mask is, as we said, or as we know, that because we are talking about microns, sub-microns levels, even in the nanometers range. Okay, you can understand the feature size of any ICs that we are making is very small. Okay, very small size. So when we are talking about a photo mask of the same size, you can understand inspecting such defects is very difficult. Okay, when we are talking about this, defects are having its width, you can say in the like 5 nanometers or 10 nanometers or 20 nanometers. This size is very small. Okay, and inspecting such defects are very difficult, very difficult. It's not very easy, it's very difficult to inspect such defects. So generally what happens is we are not making the mask of like the same size that actually we want to print onto the wafer, but rather what we are doing is we are making it 4 times or 5 times larger. Okay, if it is 4 times or 5 times larger, obviously inspecting the defects are more easy, or repairing it is more easy. Okay, so that's why what we are doing is, first of all, the mask that we are going to fabricate, that mask is actually of, sometimes, for example, I have taken in this particular slide, you can see. So what we are doing is, we are taking it 20 times larger. Okay, we can take a mask which is 20 times larger. Okay, and first we are making a mask like this, and then we are using an optical reduction system. So basically what we are doing is we are doing demagnification of your image. Okay, we have to demagnify it, and then we have to reduce the size. So what is the possibility? Actual size is this. Okay, actual working mass is having this size. Okay, you can see here it is 200:1. So it is something, I think it is maybe wrong, 200 times, or it may be 20 times. Okay, it is 20 times larger. Okay, so when it is 20 times larger, so you can see that this image is very much larger as compared to the final mask. Okay, so once we are making a mask, here the inspection of the defects and repairing is very easy. Okay, as compared to this. Okay, as compared to this. So what we are doing is, first we are fabricating a big mask, and then we can go for the means reduction of the size of the mask. And this can be done by mask fabrication by photo reduction, demagnification, and then later on we can go for the final working mask. We can fabricate, we can reduce this size of the mask. Fine. So this way it is something similar to your photography. Okay, something similar to your photography. So these are the different ways by which we can fabricate the mask. Now we can look at, there are three very important exposure mechanism. Okay, basically when we are having a mask, okay, when we already made a photo mask, then the question comes, how this photo mask will be used for optical photolithography. This is the question. So like if we want to expose our wafer, okay, into the photolithography system, then what are the different possibility by which we can expose our wafers? Okay, this is the question. So let us suppose I have a wafer here, and then if we want to expose this wafer using the some light source, and we are having a mask, then you can think of this mask may be directly in contact with your wafer. Okay, the first type is contact printing. Okay, it is contact printing. So you can see we are placing a wafer of the same size as our wafer. Okay, we are placing a photo mask of same size having the wafer. Okay, and there will be no demagnification of the printed image onto the photo mask. So it is just like 1:1 exposure system. 1:1 means whatever be the image feature size, the same size is going to be printed onto your wafer. Okay, because we do not going for the demagnification concept over here, right? And in the contact printing, this photo mask will be directly placed over your wafer. Okay, so it is having a hard contact between them. Okay, so the obvious advantage of this having is of this system is that resolution will be very high. Okay, the resolution will be very high, but the problem is what we can have is in this system is like when we uh, want to reduce the feature size, that time the volume density of your devices within the wafer will be very large, and that time when this hard contact between the photo mask and the wafer, what it will do is it will damage your photo mask as well as the wafers, and that time the defect density will be very high. So this is one of the problem. Okay, similarly this next system is again it is a 1:1 exposure system. There will be a very small gap. Okay, small gap between your wafer and your photo mask, a very small gap. Okay, in certain it may be in the certain range, like in millimeters, or it may be in some 15 to 20 micrometers or 10 micrometer and so. Okay, so that gap is very small. Again, this gap, how much gap we are keeping here, that is going to decide the resolution of this particular exposure mechanism. So this particular proximity printing is obviously it is going to means reduce the disadvantage of your contact printing, in which it is having the hard contact and it is having a large defect density because of the hard contact. But in the proximity printing, this particular disadvantage can be overcome, but still the problem is the resolution is not that too high. Okay, so the most of the time we are using the system this one. Okay, usually 4x or 5x reduction that we are doing, so which is called as the projection printing. This particular technique is most of the time is used. So any IC industry, if you see, all the IC industry nowadays are actually using the projection printing. Okay, so in the projection printing, what we do is we are fabricating a mask which is actually having its feature size 4 times or 5 times larger than the actual size. Okay, so what we do is we are having an optical system. That optical system will composed of a certain lenses. Okay, and the function of this lenses is to demagnify the image of your mask, and then a certain portion is going to be exposed by having this particular projection printing. So in this cases, we generally use a step and repeat procedure. So in this, what happens is you can see that a very small portion of the wafer is going to be exposed. Okay, due to a particular optical field. So what we have to do is, if we want to completely means uh, do the exposing, if you want to completely expose our wafer, in that case what happens is we have to keep on make the shift or movement of the wafer. Okay, so that is called as the step and repeat procedures. Okay, and that way we can do the projection printing. So most of the IC industries is actually using this one because it is having a very high resolution. Okay, high resolution can be obtained by having this one. obviously because the systems are not touching each other, like it is optical system we are using for focusing this beams, okay, and no systems are touching each other, like wafer or this mask are not touching each other, okay, so there will be no wear and tear, no contamination, and therefore defect density will be very less. But this system is very expensive, okay, remember that this system is very expensive. So one more question that we need to answer is, can we go for direct writing technique the way we have fabricated our mask? Okay, is it possible to go for uh, direct writing technique to our wafer only? Okay, we can have the wafer and we can go for direct writing technique. Okay, so is it possible or not? The answer is yes, it is possible. We can go for direct writing technique to the wafers, okay, without having the mask, okay. But the problem is that if we do not have the mask, then the rate of production is very small. The rate, it will take a lot of time, okay. Generally, if we directly use the electron beam technique or laser beam technique for direct writing technique to the wafers, okay, the writing to the wafers will take large amount of times, okay. So the rate of production of any wafer will be very small, okay. So that we have to take care of. So throughput will be very small, and to means avoid that one, what we are doing is we are using a we are first fabricating the photomask, and that photomask will be further used for your wafer exposures. So I hope this discussion must be clear. So in the next lecture I will be discussing few more points, and mostly about your photoresist. So thank you for watching today's lecture. So I will be discussing the next topic in the next lecture. Thank you for watching.